thank you very much for having me here today. Today I want to present our recent advances in TMS electric field modeling and including directional sensitivity of cortical neurons into our electric field simulations. Next slide, please. So on the left, there is a short overview about our recent mapping approach we just published in Nature Protocols. So basically, we are applying TMS pulses with the 5-second interstimulus interval at random locations and orientations over the motor cortex. And for each of the pulses, we record the motor evoked potential, as you see on top. And for every motor evoked potential, there is an associated electric field distributions we calculate. And afterwards, we are applying a nonlinear regression to each voxel in the region of interest and correlating the electric field magnitude with the MEP. And on the bottom, you see the goodness of fit value between on the cortex. And we hypothesize that the location with the highest goodness of fit resembles the cortical I/O curve, basically, and where we have the strongest effect between electric field and MEP. So this mapping approach works quite well, and we could validate it in several subjects, but it is solely based on the E-field magnitude as it is right now. And we all know that directional sensitivity plays a significant role. So when we rotate the electric field to let's say from the normal orientation to more tangential, we see that the resting motor threshold increases. So the cortical column cosine model you all might be aware of is kind of oversimplifying the whole process a little bit, and it would assume that the tangential component of the E-field would not lead to an effect at all, which is basically not what we observed so far. So Ibarra developed a realistic but very computation-intensive model by modeling these neurons and applying electric fields to them and determining the firing thresholds. But in practice, this is not really practical, because simulations take a lot of time, and in the lab it restricts the practical applicability, for example, mapping studies or dosing, where we want to have the thresholds really fast. So our goal was to derive an efficient model to determine the firing threshold within milliseconds and within basically which we can easily do during our electric field calculations. Next slide, please. So therefore, we used the approach of Arman and extended the set of neurons to more than 30. Here you see the layer 5 neurons just as an example. And we were applying different electric fields to them, homogeneous electric fields, more or less homogeneous. So we have a parameter phi where the electric field was averaged over, or the thresholds were averaged over. Theta is the basically the angle of the electric field with respect to the somatodendritic axis, and we have a potentially electric field drop over the cortex between gray and white matter surface, so over the neuron, basically what we also considered. And we calculated the electric field thresholds, Jan-Till stimulation, and action potential generation for every, let's say, different electric field parameter, phi angles, theta angles, and delta E values, and averaged them over the set of neurons to determine an average threshold map of this cell type. And next slide, please. So on the left, you see the result we get for the average map of layer 5 pyramidal cells. So on the x-axis, you see the theta angle with respect to the somatodendritic axis, and on the y-axis, you see the electric field drop. And it can be immediately seen that at tangential electric field, which means theta equals 90 degrees, the thresholds increase And you see a cut through this color plot on the right. The thresholds increase, but and if the electric field is along the somatogenetic axis, so 0 or 180 degree, the thresholds are lowest. So, and what I'm also showing here is basically the two alternative models. So the cortical column cosine model would assume an infinite height threshold at theta 90 degree, and the magnitude E model is simplifying it with an equal threshold over all incident angles. So, and in this figure, you can see that actually the magnitude E model is a little bit more precise than the CCC model, which is a little bit overestimating the directional sensitivity. So we provide these maps also for layer 2-3 pyramidal cells, and we just calculated it also for inhibitory basket cells in layer 4. And they are basically ready to use like a lookup table. So if you, in your electric field calculations, you extract the angle theta and this electric field drop along the somatogenetic axis, this delta E, you can readily apply it to your electric field simulations in order to correct for this sensitivity profile. Next slide, please. And so we also validated our model and compared it to measurement data from Victor and the Risto group. You may know they have these very fancy multi-channel transducer where they can rotate the electric field by in very small steps by 360 degree. And we compared the directional sensitivity prognosed by our model to the directional sensitivity of the motor evoked potentials they measured. Next slide, please. So the dots here now show the MEPs measured at different electric field angles, and the solid line is the prediction of our model, and the dashed line is the cosine, the cortical column cosine model. So next slide, please. If we increase the stimulation intensity from to 120% RMT, for example, you see that this directional sensitivity gets weaker. Next slide, please. And that our model still is able to replicate this behavior. And even at 140%, you see that we almost got a circle. So next slide, please. So, and finally at 160% RMT, we do not have any directional sensitivity anymore, because it doesn't really matter anymore if you have a tangential electric field, if you increase the stimulation intensity so far, so there is no, the neurons get stimulated anyway. So, and here we see that our predictions pretty well align with the experimental observations of MEPs. So what we did was we took the map now and we applied an intermediate step. So we normalized the map to a value of 0 degree electric field at 0 delta E. And so here now we can see a neuronal sensitivity map, basically. And it ranges from 0.9 to 1.2. And we weighted the electric field magnitude by this sensitivity map and got an effective electric field. And this sensitivity map means basically values smaller than 1. We have an effective efficient electric field which stimulate neurons efficiently, and a value greater than 1, we have kind of an inefficient electric field. So we need potentially more electric field magnitude in order to stimulate the neurons actually. And what we did was we simply weighted our electric field distributions now in this new additional step, and performed the regression as before with the effective electric field and not with the raw electric field, I would say. And our hypothesis is that we could decrease or explain more variance in the data, basically. And next slide, please. In most of the subjects, the results didn't change much, but we also have a kind of subjects where we see that the hotspot we determine was basically stronger. So we have higher R2 scores with the effective electric field model, and also that the hotspot might change its location. So this is currently an ongoing study, and yes, I'm really excited how this will approach. Yes, and so anyone who is basically working with electric fields and optimization could include this sensitivity map to get a more precise estimation what the electric field is actually doing, and so how effective it actually is. So the magnitude alone might be corrected in the future. Thank you.